This Math156 script is a little bit optional and off the record. The topic isn't discussed in any detail in the textbook, but it's one that I'm fond of, and I've got a nice example. It's the hypergeometric distribution, which is, in a very specific case, better than the chi-squared distribution for modeling what's going on. So here's the classic hypergeometric distribution example, which actually occurred. When my grandchildren Thomas and Catherine were very young, we flew off to England with their mother, Lisa. We were sitting around in Logan Airport. The kids got hungry, so Lisa went off and bought 6 munchkins from the local Dunkin' Donut stand. 2 of them were chocolate, 4 of them were plain. She picked 3 of them at random and put them in the bag for Thomas. And Thomas, of course, being a thinking kid, asked, "What's the probability that I've got no chocolate munchkins, 1 chocolate munchkin, or 2 chocolate munchkins?" And this question is answered by the so-called hypergeometric distribution. So d hyper 0, 2, 4, 3 means the probability that Thomas got 0 of 2 chocolate munchkins, given that there were 4 non-chocolate munchkins and there were 3 munchkins put in his bag. And by changing the first argument, you can get this probability for 0, 1, and 2. You can check for yourself if you like. These probabilities are 20%, 60%, and 20% respectively. And of course, since R deals nicely with vectors, you can get them all in one fell swoop. Well, with hungrier kids, you could imagine 30 munchkins, 10 of which are chocolate, and Thomas gets a bag containing 15 of them. What are the probabilities for 0 through 10 chocolate munchkins? Exactly the same function will give this result to us, and we can make a nice bar plot of the number of chocolate munchkins. Now, of course, we've got sibling rivalry here, and Catherine says, Thomas got 7 chocolate munchkins. That's not fair. How do you answer that question? You say, well, suppose these were distributed completely at random. What's the probability that he'd get more than 7 of them? And p-hyper will calculate that for us. And with lower dot tail equals false, so it gives the probability of more than 7, it says there's only a 2.5% chance that he's going to get more than 7. And furthermore, the probability that he'll get 0, 1, or 2 is also about 2.5%. So the probability of such an unequal distribution is about 5%. It's unlikely that this would arise by chance, but by no means impossible. In fact, we can make up the entire contingency table for this situation. And here's what it looks like down at the bottom. Thomas gets 8 chocolate and 7 plain. Catherine gets 2 chocolate and 13 plain. And this is a natural for a chi-squared test. We run a chi-squared test on it, and it says the probability that this unfair distribution would occur is about 5%. But there's also built into R an exact test of this based on the hypergeometric distribution. It's called Fisher dot test, and it says the probability of such an unequal distribution is what we just calculated, 2.5%. So if you've got a hypergeometric distribution problem like this, the Fisher exact test really does a much better job than the chi-squared test. The chi-squared test is a fairly good approximation in lots of situations, but in this one we can get the exact results. Of course, we can also do this by simulation. We make a flavor vector with 10 chocolate and 20 plain, and then we make a child column where we have 8 Thomases and 2 Catherines opposite the 10 chocolates, 7 and 13 opposite the plains. And now we can make a data frame where we have two columns, flavor and child. We can make a contingency table out of that, and it's exactly the contingency table that we've been working with. We could call a chi-squared test on that, but we can also do a permutation test. 10,000 times we will permute the child table, thereby dividing these chocolate munchkins 10,000 different times between the two kids, and each time we will permute the flavor column, thereby giving a different assortment of chocolate and plain to each kid, and figure out the result, which is the probability that the permuted one comes out to be chocolate and the child is Thomas. We can make a bar plot of this, and it looks mighty close to the hypergeometric function, because basically we're simulating exactly the situation described by the hypergeometric distribution, and therefore it's no great surprise that if we calculate the probability that the result is greater than or equal to 8, we get something that's pretty close to the 2.5% that we found earlier. Notice this is what statisticians call a one-sided test. We're addressing the issue of whether Thomas got too many chocolate munchkins, rather than the question of whether the number he got was unreasonably unlikely, either through being too large or too small. Now let's try this on some real data. I'm going to load up this general social survey from 2002. I think there are far more recent examples of this, and you might even be able to base an interesting midterm or final project on one of these social surveys, because it's got answers to questions about lots and lots of political issues. We need to get rid of the various levels that we don't want and cut it down to what we're interested in. I won't go into the details of this, but just show you that we can end up with a table where for gun owners or non-gun owners, we have the number that voted for Bush in 2002, we have the number voted for Gore in 2002, and we've got the row sums and the column sums built in to the table. Now the question is, do these data indicate that gun owners are more likely to vote for Bush than for Gore? It certainly looks that way, but maybe we can attach a p-value to this result. So this is just like the Munchkin problem. Bush is like Thomas, Gore is like Catherine. Yes, I own a gun is like chocolate munchkin, no is like a plain munchkin, and I can ask for the cumulative probability distribution of the observed results from the table. And what do I get? I get 2.4 times 10 to the minus 7. That says that the probability that gun owners would be that likely to have voted for Bush is about 2 times 10 to the minus 7th if gun ownership were assigned randomly to Bush voters or Gore voters. In fact, you can use Fisher.test because this is built right into R. So you just say the table with alternative equals less, so you get a one-sided test, and you get exactly the same number. We can also do this by simulation, which I kind of prefer. So when you run chi-squared on this, you get a result that is about twice as big because it's a two-sided test. And now we can simulate the distribution of guns. So let's make a data frame where we have a gun column and a president column, and sample 10,000 times from that. And the statistic that I'm going to use is the number of guns that are in the hands of Bush voters. So we'll do this 10,000 minus 1 time. We will permute the gun column. That is, we will take the column about gun ownership and scramble it. So now guns are assigned randomly to Bush or Gore voters. And we will compute the fraction of the time that this permuted gun column says yes, a gun is owned, and the presidential candidate voted for is Bush. And now we'll make a bar plot of that result. This is another hypergeometric distribution. And now we can ask, what's the probability if we randomly assign the guns to voters that more than 140 of these guns show up in the hands of Bush voters? And the answer is about 10 to the minus 4th. Now you say, that's substantially different from 10 to the minus 7th. Sure it is. What this means is 10,000 times I tried scrambling these guns, and under no circumstances did I put more guns into the hands of Bush voters than the actual number of guns that turned up in the hands of Bush voters. I'd have to do of the order of 10 to the 7th simulations in order to get the p-value that came out of the Fisher exact test. And the Fisher exact test gives us this 2.3 times 10 to the minus 7th that we got out of our chi-squared, out of our hypergeometrical analysis. And that's the end of this script.